Understanding binary is fundamental to understanding how computers work. Today we are going to look at how we can use binary to represent numbers. A long time ago, you learnt about a number system just like binary, but the one you learned about was called denary. This is the one you use every day in your maths lessons. Now denary, if you didn't already know, is base 10. This is because it has 10 different symbols. Here they are, look. 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. 10 different symbols. Now how does denary work? Well, let's look at this number here. If we break it up, we can say that this number on the end represents the number of units, or the number of ones. We say this number, the second number from the right, represents the number of tens. We say the third number from the right represents the number of hundreds. And finally, we say this final number here represents the number of thousands. Okay, now this is a pattern. Can you work out what that pattern is? Of course, it is powers of 10. Okay, so if we just write those in, I'll write them just below, so I'm in that room up there. Anything to the power of 0 is 1. This one is 10 to the power of 1. This is 10 to the power of 2. This is 10 to the power 3. And if we were to continue, if our number was bigger, we'd have 10 to the power of 4, 10 to the power of 5, 10 to the power of 6, and so on. Binary works in exactly the same way as denary, apart from the fact that it's base 2. This means it only has 2 symbols, 0 and 1. A question for later on is, why does a computer only have 2 symbols? Okay, but for now we're going to concentrate on this binary number. How do we work out what that represents? Well, we do exactly the same that we did with the denary number. We break it up. But this time, because we're working in base 2 and not base 10, we're going to do powers of 2. So this one represents 2 to the power of 0. This one represents 2 to the power of 1, 2 to the power of 2, 2 to the power of 3. All right, which means this represents the number of 1s, as we did before. This represents the number of 2s. This is the number of 4s. And this is the number of 8s. Okay, so that means we've got 1 times 8, 0 times 4, 1 times 2, 0 times 1. If we add all them together, we get 10. So this binary number, 1010, represents the number 10. Now it's your turn. Can you work out what the following binary numbers would be in denary? Okay, so let's check your answers. Let's draw in our lines. So this is our number of 1s, this is our number of 2s. So this one equals 2. Let's do the same with the next one. Draw in our 1s, our 2s, our 4s, our 8s. 1, 2, 4, and 8. So this one would be 8 plus 4, which is 12, plus 1, which gives us 13. The final one's a bit longer, but we just do exactly the same thing. We break it up. This is our number of 1s, this is our 2s, this is our 4s, this is the number of 8s, this is the number of 16s, and this one is the number of 32s. So here we've got 32 plus an 8, which gives us 40, plus 4, which is 44, plus a 1 equals 45. Is that what you got? Trying to work out what a denary number is in binary just means doing it exactly the same way, but in reverse. So this time we're going to start with our 1s, 2s, 4s, and 8s. So I'm going to write those in. 1, 2, 4, 8. Okay, and the number I want to make is 12. So, does 8 go into 12? Yes, it does. Leave me with 4, so that goes in. I don't need a 2, and I don't need a 1. So 12 equals 1100. Can you work out what these denary numbers would be in binary? Okay, so let's go through your answers. Let's start by building a table. We've got up to 75, so we'll have to go up to 64, 32, 16, 8, 4, 2, and 1. Just organize our table. Okay, so calculating 5, we obviously don't need a 64, we don't need a 32, we don't need a 16, we don't need an 8, we do need a 4, we don't need a 2, we do need a 1, giving us 101 as our answer. 23, again, we don't need a 64, we don't need a 32, we do need a 16, if we add a 1 to an 8, if we had an 8 that would be too big, so we don't need an 8, we do need a 4, we do need a 2, and we do need a 1. So 23 would be 10111. Finally, 75. This time we do need a 64, and we've got 11 left to make. So we don't need a 32, we don't need a 16, we do need an 8, we don't need a 4, we do need a 2, and we do need a 1. So 75 would be 1001011.